Okay, good morning and welcome to this Measurement for Manufacturing webinar. I'm Michael Stones, the PowerInspect product marketeer, and I'm joined by Peter Storey, a PowerInspect applications engineer, and today we're going to talk to you about measurement for manufacturing, how we can use measurement technology to improve our manufacturing performance, to increase the efficiency, and to minimize our costs. So if we just have a quick look at the agenda for today's presentation. So I want to start by just giving you a brief overview of PowerInspect to talk to you a little bit about our background as a software, what we do, and the types of industries and areas where we work. And then we'll move on to look at the main part of today's presentation. So what we wanted to do here was talk to you about some of the experiences and some of the challenges that our customers often face. And we're going to show you how we've worked with customers in the past to solve problems of part setup and process consistency and part certification. Then of course we'll summarize the points that we've made in the webinar, and there will be time for any questions at the end. If you do have a question throughout the course of the webinar, please use the question panel on the right hand side, post your comments there. We won't address the questions until the end of the webinar, but please make your questions then, and again at the end if you have any additional questions then you'll have the chance to ask them at the end. Okay, so let's have a look at the background of PowerInspect. So here we've grouped PowerInspect's applications, our measurement applications, into three groups. We've got measurement, so that's a traditional inspection. You'd be talking there about inspection of parts, tooling and structures. So it might be used for CAD comparison or for identifying the size and position of geometric features. In addition to that, PowerInspect is used for basic reverse engineering functionality. And of course, one of the main topics for today's presentation, it's improving process accuracy. And what we're talking about there is quantifying and compensating for process variation. That's something that I'm going to touch on later in the webinar. It's used in part assembly and fixture calibration. And PowerInspect can be used for part setup, and that's something that Peter's going to show us in a minute or so. It's used as feedback for automated processes. Now, we're aware in PowerInspect that there are a range of different measurement applications, and that different measurement hardware is suited to these different measurement applications. So for example, on the shop floor, we've got the versatility, the flexibility that PowerInspect can work with a measurement arm, so companies like Faro and Hexagon Metrology, and laser scanners from the same companies. But in addition to that, we might be looking at large volume metrology, and we can also work with PowerInspect not only on the arm, but we can work with laser trackers from companies like Leica and Faro again, and from API. In addition, in that large volume metrology arena, PowerInspect can connect to optical devices from Metronor, and of course we work in the inspection room on manual CMMs and CMT CMMs. So one of the benefits of PowerInspect, one of the real things that we like to sing home about, things that we like to talk about, are that it's flexible and it offers you the interoperability that you can confirm results by using different hardware. So in the top left hand side you can see PowerInspect being used on a horizontal arm CMM, and that's very common for us in the automotive industry. And of course, let's not forget machine tool probing, another area where PowerInspect is very powerful. So the main point to take there from the overview of PowerInspect is the real versatility and flexibility that we offer in our measurement applications. So there's enough about PowerInspect. Let's move on to the main topic for today's presentation. We said we're going to talk about solutions for common manufacturing problems. And first of all, Peter's going to talk to us about part setup and how PowerInspect can be used to increase your efficiency in part setup and optimize those machining programs so as to improve your manufacturing performance. Then we'll look at process consistency, and we'll conclude by looking at how measurement in terms of part certification can reduce your costs. So if I now hand over to Peter, and he's going to talk to us about how measurement technology can be used in part setup. Over to you, Peter.
Okay, thanks Michael. I'm assuming you can hear me okay. Have you muted me as well? Okay, great. Thanks Michael. Yeah, hello everyone. My name's Peter Storey and I'm an application engineer here in PowerInspect. So the first problem that we're going to look at today is part setup and how our customers are looking to reduce lengthy setup times on their CNC machines. So now, manual setup of workpieces requires a very skilled operator and is highly labor intensive, meaning it can take up to several hours to align some parts, which equally makes scheduling very difficult. This is particularly a problem in industries manufacturing very large, very heavy parts that make them even more difficult to align and to move, such as the marine and aerospace industries. It's also useful for parts that have undergone heat treatment or other processes that may have resulted in some sort of deformation. Okay, so our solution in PowerInspect is our delta transformation functionality, which allows you to calculate, then export the difference in translation and rotation between any two alignments. With PowerInspect, you can do an approximate alignment by eye, then probe your part using either an on-machine probing tool or a portable CMM, and then use this delta transformation process to tell your CNC machine to account for any small misalignment. This means what you're effectively doing is moving your NC code to the part rather than moving the part precisely to your NC code. So how exactly do we do this? Well, we've got a short video demo for you now which will explain the whole process. So here we have a part that needs to be mounted on our CNC machine for us to do some further machining processes. Note that this is a relatively simple part for the purposes of this demonstration, just to show you guys how this works. So we've already created some probe paths, which we're going to be using for measurement of any misalignment, and then from that calculating the true alignment to update our machine toolpaths. We simulate the program now to check for any collisions. In this case, of course, there are no collisions present. So once this is completed, we can go ahead and export this probe path for use on our CNC machine. So we open up the probe path export dialog, and then we're required to just enter a few details for post-processing. So we enter a part name here, and then we also need to make sure that our workpiece offset is correct. So in this case, it's G55. All okay, so now that that's done, our code can be exported, and we'll just show you what this code looks like. And here we go. So this is the code that's going to be played on our CNC machine. Now on the machine, we insert and chuck our workpiece by hand so that it's roughly aligned with the correct axes, but we know that this isn't going to be good enough for further machining just yet. We'll then run our inspection routine using our on-machine probe in this case. The results from this inspection routine are saved on the control, and then we can read these straight back into PowerInspect. Okay, so now we're back in PowerInspect. We open up the results file, and then you'll be able to see in a second that there's some deviation of these points from the nominal values. Now, as you can see here with the blue and red confetti showing that there's some deviation up to about 2.3 mil as the largest deviation. So roughly aligned with the correct axes, but naturally this isn't good enough for us to do any more machining processes just yet. So it's now time to create our best fit alignment. So we use all the points from our inspection and then use a fitting type min-max to try and fit all our points within our predefined tolerance band. We click OK, then we can go to our best fit item and then play this item. Then within here, the best fit analyzer will now run to see if a solution exists. And as you can see, the analyzer has done a great job of fitting all the points within tolerance. So now there's just a few microns deviation from the normal value. So we're happy with that. So it's now time to create our delta transformation item. So we grab that from the miscellaneous toolbar. We want to update our machine coordinate system with a new location. And then we want to reference that best fit alignment that we just created with respect to our initial alignment, our user-defined alignment in the vise. From here, we can now export this transformation as NC code, as a workplane into PowerMill, or as an IGS file for using any other CAD system you might be using. But in this case, we just want to export straight away to NC code to use on our CNC machine. So with all that done, we can send our NC code to the CNC machine. The toolpath will be updated with the true location of the part, and we can continue machining with confidence. Okay, so to give you a real-life example of where our part functionality, our part alignment functionality is being used, we have a customer who are working with titanium forgings. Now with forgings, there's always some very small variation from part to part, and impurities tend to solidify on the outer layer of the forged part. So our customer requires that their workpieces are aligned on the CNC machine such that a small slither of material is removed over the entire part. So to do this, they'll probe the workpiece, then use a fitting method that ensures that all their probe points are outside their lower tolerance limit, so that material will be removed all over. Okay, at this point I'm going to hand you back to Michael, who's going to talk you through process consistency.
Okay, Peter. Thanks for that. So really interesting there. I think it's very highly applicable for when we're working with free-form parts there, or with complex 5-axis parts, so we can use this part alignment, this delta transformation functionality to optimize the machining program, and so that we're matching up the part coordinate system and the machine coordinate system. So anyway, we now move on to problem number 2, and that is process consistency. So what we've tried to do here is to give you an example quote of things that we might encounter with a customer, and then I'm going to talk to you about how exactly we go on to solve that problem, how we might analyze the problem, and how we then go on to solve it. So as you can see on the screen, the example quote from the customer is that they're working with high value components and long production runs, and that over the batch of components the quality of the process fluctuates, often causing certain features to be outside of the specified tolerance limit. Now really this quote's a little bit contrived, and I should perhaps add that in this process consistency category there are really 2 common problems that we come across with customers. You've got customers who are working with smaller components where there's a high machining rate, a high throughput of components in the process, and then you've got customers who experience process variation and they're working with larger parts. So what's the problem? Well, the problem is that there's variation in the process, and at this point I'd just like to quickly reflect back on a webinar that we gave earlier in the year, and that was, I invited a colleague from Coventry University, Ian Wilcox, a senior metrologist, a man that's very experienced in metrology, having worked with a lot of leading automotive OEMs. And Ian came to talk to us in that webinar about variation in the manufacturing process. And what Ian explained, you can find this webinar on powerinspect.com/webinars, and I'd encourage you to watch it. It's a very good session. But what Ian explained is that variation can arise from these 5 E's. And two of them that he mentioned were equipment and environment. And if we reflect back on that problem, let's just jump back a slide. So if we reflect back on that problem, so we've got problems here with process variation coming from the equipment. So that might be the smaller components that we were talking about with a high machining throughput. And there you might get a problem such as tool wear or deflection. And what happens is, because we've got such a high rate of machining, that over the batch of components, tool wear causes certain features to become out of tolerance. And then the second problem that we come across is with larger parts where environmental causes might cause the process to fluctuate. So that's things like if there's an increase in the ambient air, ambient temperature, so that would cause components in the machine and the component itself to expand, and thus the machine coordinate system can't be relied upon to define the true position of the part coordinate system. So how do we get past these problems of tool wear and deflection or thermal stability? What can we do with measurement, and how can that help us to improve our performance? Well, machine tool probing can be used to monitor tool wear, deflection and thermal stability. So how this works is that you would locate a critical reference feature where perhaps there's a lot of machining, and after that feature has been machined, then you call up a probe change, call in the machine tool probe, and you probe that feature. Those results are then stored in the measurement software, and as I'm going to show you in a minute, can be exported to Microsoft Excel to monitor the results for process drift. And one of the real benefits here is that by having greater control over the machining environment and over the process, it allows us to run unattended machining and lights out machining. So let's just contrast that with how we might have done it otherwise. So if we were to inspect post-machining process, then the fluctuation from the tool wear or from the thermal expansion wouldn't perhaps be identified until after we've machined 10 or perhaps even 100 non-conforming parts. And then of course that's a real problem for us as a manufacturer, in that we might even have to scrap the parts, or we'd have to put them back onto the machine for rework. Whereas by contrast, if we use this process consistency, this solution that we're presenting here, using the machine tool probe to monitor the tool wear, deflection and thermal stability, then what we can actually do is we can insert some logic into the machining program. So we might be machining board number 1 on a part. We can then insert the logic into the NC code that it performs the tool change, that it probes that bore, and then uses the results and says in the code, is that feature in tolerance? Yes, no. If it is in tolerance, then we can go on to machine bore number 2, then change again, probe change, bring the probe in, is it in tolerance? Yes or no. If it's not in tolerance, then we can say, okay, we need to do some more machining. So what are the benefits of this? Well, one of the key things here is that it allows you to intervene before producing non-conforming parts. So of course we talked earlier about the post-process inspection option, where we might not be able to monitor that fluctuation in process until it's too late. If we probe in process, we can use the data that we export to Microsoft Excel and statistical process control to update the machining coordinates if necessary, or we can create a local part datum, which gives us, of course, increased accuracy. One of the other benefits is that it allows us to increase the range of environmental conditions in which the machine can work. So this is really key when we're working on larger parts where thermal stability might be an issue. And by compensating for changes in the environmental condition, then we have greater control again. We reduce the variation in our machining program, and we can ensure that features are within tolerance. So overall, we can say that this is a proactive approach and that it minimizes the scrap at the end of the process and minimizes your rework, saving you both cost and time. So let's just jump in here, and have a look at this on a video that one of my colleagues created for me. So what we've got here is a part that's it's only a demo bot, but it's already got some probe features. We call up the SPC, Statistical Process Control add-in, and then what we can do here is that on the left-hand side of this dialog, we've got our different inspection groups. You've got a geometric group and a surface inspection group. And on the right-hand side, we've got all the parts in our batch. So you can see there part number 2, 3, 4, 5, 6, etc. And these are new measures in PowerInspect. So from the left-hand side, we select the features that these critical reference features we're interested in. We don't necessarily need to select every feature to monitor the process consistency. There might be a certain feature where we're doing a lot of machining, or there might be certain areas of the part that we know are key. So we select them, and then we can export them to Microsoft Excel, as you can see on the screen there. And what we've got across the top in the columns of the Excel are the different parts, so the different new measures across the batch in PowerInspect, and each of the rows is a certain feature that we're interested in. And what we can do is we can use this data here in the middle. Here we are in the middle. We can use that data to monitor how the process for a certain feature might fluctuate across the batch of components. And if we identify that it's getting close to our tolerance, or if we need to intervene, then of course we can update the coordinate system, or we can create a local part datum. Okay, so on to problem number 3, the final problem that we're going to look at. And this is really back to what we think about when we're talking about inspection. We know in PowerInspect that in general, customers are demanding parts are manufactured to ever tighter tolerances. And we know that you, as manufacturers, need to prove that you've made what you think you've made, that parts conform to the design intent. So we understand that by using measurement technology, by using PowerInspect and other measurement solutions, you can document processes and demonstrate the part quality before shipping it to the customer. You can include a report to verify the dimensions and geometry. And there's 2 ways you can do this in PowerInspect. As you can see on the video that's playing in the bottom left-hand side, you can use this to record geometric feature size and position. So we can report on the radii of features, or the X, Y, Z coordinates of a feature. And of course we might want to report on the surface properties of our machining. So here we'd perform a surface inspection, and you've got direct feedback on the screen with geometric confetti that gives you a different color, whether that feature's in tolerance, out of tolerance, or acceptable. Sorry, above tolerance, below tolerance, or acceptable. And up here on the top right hand side, you can see the color scale that I'm just hovering the mouse over. And that allows you to make things simple for management and the customer to understand that a green point is acceptable and that a red point is not, and a blue point is not. So the benefits of this are that you can document your processes. it gives you confidence in what you've made, and it allows you to demonstrate that your part conforms to the original design intent. It conforms to the CAD model. Now if I hand you back to Peter, he's just going to take us through a quick demonstration in PowerInspect of the different things that we can include in our reporting. So back over to you, Peter.
Okay, great. So yeah, as Michael says, I'm just going to build on what he's been saying just now and give you a quick demo to show you how easy reporting is within PowerInspect. So we've got a PowerInspect file here with some features that have already been measured. Now say we want to create a report to show to our customer on the results of our inspection. Let's just jump into our report tab here. And now you can see the results from our inspection group and from our geometric group are already in here. But it's not particularly informative at the moment. It's just a list of names and numbers, which doesn't really say much to someone who's seeing this for the first time. So what we can easily do is create a CAD view to add to this report. So if we head back to our CAD view tab, let's just clean this up a little bit. We can hide our tool, zoom in, and then we can show labels to give a bit more information. Now this is still quite a lot of information, so we can hide our geometric group and zoom in once again. So now we can just see the results from our inspection group. Now the green confetti is showing that all the points are in tolerance, so maybe our tolerance band is a bit too large. So what we can do is we can go to our inspection group and click modify, and that's just reduce down our tolerance band a little bit. Update existing points and then click OK. So now that just gives us a bit more information about where the larger deviations are. I'm not happy with that point there, so I'm just going to I can just drag that up using manual labels. Okay, I'm happy with that, so I can now go to create a CAD view report from the miscellaneous toolbar. I click OK, and you can see this item is now added to the end of the report, to the end of the sequence tree. So if we jump into the report will refresh, and we can scroll down. You can see that that's been added to the end of the report as well. Now it's not particularly informative down there. We want it really in with our inspection group. So what we can do is we can either drag it up the sequence tree and it will be moved in the same way in the report, or we can right click and transfer to inspection group. Now by doing this, the CAD view is added to our inspection group, as you can see here in our sequence tree, and that means that the CAD view is added to every page that contains results from our inspection group. So as you can see on page 1, surface point 1 just fits on there, so that first point is just shown there. And if we go down to page 2, surface points 2 to 12 are shown here in the CAD view. So that's a lot more informative for someone who's seeing this for the first time. We can do similar things with our geometric group. So let's hide our inspection group and show our geometric group. Let's just rotate our CAD view around. That's better. So these labels are these labels are not quite on the screen, so I can drag those in. I'm happy with that. So the last thing I'm going to do is add some dimensions to this. So we can go to our dimensioning icon and then easily click where we want to add dimensions, so we can create the distance between two circle centers, for instance, or the angle on this cone, simply by clicking and dragging. Okay, I'm happy with that. So again, once again, I can go to create a CAD view report item, and then once again that will be added to the end of our report. So that just gives you a very quick idea of the very basics of what we can do within PowerInspect for reporting. I'll now take you back to our PowerPoint presentation where Mike's just going to give you some closing remarks.
Okay, Peter, thanks for that. So just to summarize what we've looked at today. So we began by seeing how probing with portable devices or with the machine tool probe can improve setup accuracy. So that's using the part location to optimize the machining program. And of course, by optimizing that machining program, we're saving ourselves time and money in the machining process. Then we moved on to look at in-process probing, increasing process repeatability. So that's monitoring a feature after the cutting process, probing that, and using that information to update the coordinates in our machining program so that we don't exceed tolerances. And then of course Peter's just shown us a very quick demo there, which was quite neat actually, about documented reports with annotated diagrams to verify the conformance to the design, the final part of this manufacturing webinar. If you'd like to find out more about how PowerInspect can be applied to manufacturing situations to improve the process efficiency, then you can visit us online where you can read more about the topics we've discussed today. And that is powerinspect.com/y-measure. There you can read about PowerInspect in 5 manufacturing situations, from final inspection through optimizing machining programs to automated manufacturing and process repeatability. So that brings us to the end of today's webinar. And does anybody have any questions? You can either ask them now, or if you've got any general discussion and feedback, then that's very important to us because it helps us to build our future webinar program. Then you can discuss those on the PowerInspect forum or on the Delcam AMS LinkedIn group. For any specific questions and detailed feedback, then please get in touch with us at mds@delcam for myself, or if you want to speak to Peter, then you can email him directly at pes@delcam.com.